Okay, so we're going to be talking about combinations here and kind of combination theory. This has a lot to do with encryption, so like passwords or combinations. A lot of things on the internet have to do with like giving you a unique password or ID. There's a certain amount of combinations that there can be. There can be people trying to hack your passwords by trying to figure out, what are all the different combinations of something that can exist. I'm going to try them all. So let's talk about a deck of cards. I do not have a deck of cards on me. I have a stack of Post-it notes, but let's pretend these stack of Post-it notes is a deck of cards. So there's 52 cards here, 52 Post-it notes. And if I wanted to say, like, in a hand of, I'm going to show my like gambling ignorance here. Let's just say a hand of blackjack is you have four cards, or some game where you have four cards. You're trying to make a good hand, good combination of four cards, and you want to know how many different combinations of four cards are there. How many different combinations could I get? Well, let's think about it this way. You pick one card off the deck that had 52 different possibilities. Okay, right? Because there are 52 cards there. You could have got any of them. So there were 52 possibilities for the first card. How many possibilities are there for the second card? Well, one of the cards is missing. So there's 51 left. So there's 51 different ways that card could have turned out. Okay. What about the next cards? Well, after that, we'd have 50. And we'd have 49. Okay, so let's go ahead and just waste a bunch of note cards here. So we'd have 50, 51. Actually, I'm not going to waste them. I never use these. I'm a hippie. So 50 times 51 times 50 times 49, essentially. If you think about like a tree diagram, your first branch doesn't go heads or tails. It goes to 52 locations. And each of those 52 locations branches off into 51 directions. So for just two of these, you'd have 52 times 51. Okay. For a third one, you'd have to do times 50, then times 49. So that's how many different combinations you could get, essentially. Now, how do we write? What's kind of the way to write this? Well, there's a way that's different than this. And this is fine, but there's a way that's different than this that's called a factorial. Okay, so a factorial is basically like if you put an explanation behind a number, that means you're going to take that number and multiply it by every number smaller than it. So if I said 5 exclamation point, that would be 5 times 4 times 3 times 2 times 1. Okay, so how can I write this? Well, I'm going to write it like this. 52 factorial over 48 factorial. Now, why would I write it like this? Well, let's see what it looks like if I expand this out. Well, 52 factorial is 52 times 51 times 50, 49, 48, 47, all the way down to times 1. 48 factorial is 48, 47, 46, 45, 44, all the way down to 1. Okay. Now, what cancels out? Well, basically, the 48 factors on the bottom, 48, 47, 46, all the way down to 1, those all cancel out with these ones, and we're left with just these. Okay. So this kind of like division of factorials, 52 over 48, it's kind of just a way to say 52 times 51 times 50 times 49. It's a way to say that like we're going to multiply everything from 52 through the number right above 48. Okay, we're going to get rid of all the numbers after 49. We're going to get rid of 48, 47, 46, 45, but we're going to be left with everything else that's higher than this number. Okay. So that's a way to just suggest I start with 52 options, then I go to 51 times 50 times 49. Okay. Now, there's a slight issue here. We want to know the unique hands. So I'm going to say these are our 4 cards. Okay, we have four cards now that I'm representing with 4 different colors, so we can keep them apart and they don't look the same. Now, how many ways are there if I get these 4 cards? Let's say this is a 2, a 3, a 4, and a 5. Well, what if I had pulled, and let's say they're all, even though they're not the same color, let's say they're all hearts. 2 of hearts, 3 of hearts, 4 of hearts, 5 of hearts. What if instead of these 4 cards, I had pulled 5 of hearts, 4 of hearts, 3 of hearts, 2 of hearts? Or if I had done 2 of hearts, 3 of hearts, and then I pulled the 4 of hearts, and then I pulled the 5, then I pulled the 4. What I'm saying is that like there are many different ways that I could arrange the same 4 cards, so I could get the same hand many different ways. That's the same idea as like there's many paths you can take on those tree diagrams that give you the same outcome. There's many different volumes or areas in the area model that are the same area, but you get them by multiplying different things. So we want to figure out like how many combinations could I get of these 4? If I just rearrange these, how many different ways could I rearrange these and mix them up and still just have these 4 items? Well, let's pick one item and call it item number 1. So if this one was first, then any of these ones could be second. Okay, so we'll pick one to be second. If this one was first and that one was second, then either of these 2 could be third, and I'll pick one of them. And once we know the third one, then the last one has to be the 4th one. So let's kind of look how that turns out in a tree diagram. If I pick this one first, then there are 3 options that I branch out to. One of these 3 is my next one. I'm trying to get this all on the page. So if I pick the black one first, one of these 3 will be my next one. It branches out in 3 directions. If I pick the green one second, then these 2 branch out below it and become my third options. Okay. Same thing would happen if the red one was my second one. Same thing would happen if the blue one was my second one. The other 2 branch out. So let's think about that branching. We start with 1, and we're going to multiply it by 3, and then we're going to multiply that by 2, and then whichever one's left, the last one just goes below it. So we're going to do a factorial. We're going to do 3 times 2 times 1. Okay. Now, the black one wasn't the only choice we had for the first one. We could have done any of these 4. So really, our first decision in our little tree diagram where we start, from one place and we branch out. Sorry, this is rolling around a lot. Our first decision is basically this. It's like, do I go here, 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 or here? So we have 4 options at first. Okay, whichever one of those we pick splits into 3 options. Okay, it could be any of them that we pick. It's going to split into 3 options. So we're going to have 4 times 3 times 2 times 1 different combinations. And actually, I'm going to introduce a vocabulary here. Different permutations of the same combination. So a combination would be like these 4 items are combined, but the different versions of how you combine them are called permutations. Okay, so we're going to end up with 4 times 3 is 12 times 2. We're going to end up with 24 different ways to make this same group of 4. Okay, well, let's go back to our example with 4 cards then. So if any hand I had 24 different ways that I could make it, what that means is I should divide by 24 to figure out how many unique hands I can have. Because if there's 24 of these that are these 4, cards or whatever, then you can't count all 24 of those and say that there's 24 unique ways to have these 4. Sorry, I'm kind of talking over myself here. If there are 24 ways to arrange these pens, then I need to say that those 24 ways do not each count as a separate hand of cards. We're going back and forth between my examples here, but these were representing cards I could pick originally, right? So I have a hand of cards of 2, 3, 4, 5 hearts, something like that. If I rearrange those, it still counts as a 2, 3, 4, and 5 of hearts. It doesn't matter if I say it one way or another. So I need to divide by all those different ways I could get that 2, 3, 4, and 5 of hearts. Well, the ways that we could do it was 4 factorial. It was 4 times 3 times 2 times 1. So what we're going to do is we are going to divide by 4. Now, I think when I was getting ready for this, it looks like I did 5 instead. So I figured out how many you could do with 5 permutations. So anyways, this would just be an example for if you were drawing 5 cards. I'm sorry that I'm not lining this up perfectly, but just make that adjustment in your head. So we would be going, it's right up here. So for 4 cards, it'll look like this. 52 factorial over 52 minus 4 factorial. Remember, this part right here This part right here is just this part. It's just signifying we only want to do 4 choices starting with 52 options, then 51, then 50, then 49. That's what this chunk was. This part on the bottom gets rid of all these common factors. Now we also need to divide by how many different combinations, which was, gosh dang it, which was, 4 factorial, or 24 different combinations. Okay, this would tell us in the end what our final amount of possible unique combinations is. All right, now let's generalize that into a formula. So if I have 4 choices, if I have, with the deck of cards, I'm starting to lose my clarity on this lesson as I'm talking through it. If I've got 52 cards and I'm going to choose 4 of them, this is how this notation looks. We say 52, choose 4. This is that notation that we saw at the very beginning in the binomial formula. It was these little C's and letters on it. Okay, so what this is signifying is you have this many things to choose from. You want to choose this many of them, and you want to know how many combinations am I going to get. Okay, so your combination formula is generalized to this. N stands for the number of options you're picking from, so like 52 cards. Okay, R stands for how many of those are you going to pick out. So we say the formula that we just wrote was the number of cards in this position and in that position. The number that we picked out was here and here. So we have n factorial over r factorial times n minus r factorial. Okay, so take a moment to just kind of look over those numbers, see if you can do that. Maybe replay this video a little bit to hear that explanation again. I know it kind of got jumbled in the middle, but this is our general formula for the amount of combinations that you can get when you have a certain amount of choices to choose from and you make a certain amount of choices. So you have 52 cards to choose from and you pick 4 of them. All right, now I want to just look at like a more general situation about choosing and just see how this formula applies. So this is going to be 3 options, choose none of them. 3 options, choose 1 of them. 3 options, choose 2 of them. 3 options, choose 3 of them. So how many ways is there to take 3 options and choose none of them? Well, there's only one way to do that. You don't choose anything. Okay, that one sounds a little weird, but just understand it in the context of the other ones as we go through. Let's say you have 3 things to choose from, 3 pens here, and I just want to choose 1 of them. Well, I can choose the first one, I can choose this one, I can choose this one. There's 3 different ways I could choose one thing out of a group of 3. 3 different ways. That's the solution. I'll go through these in a moment. If there are 3 things to choose from and I want to choose 2, well, I could choose these 2, I could choose these 2, or I could choose these 2, right? There was once again 3 different ways to choose 2 out of 3. Okay, how many ways is there to choose all 3 out of 3? Well, there's only one way. You pick all 3 of them, right? You don't have any other way to do it. You have to pick all 3. So if we take these into this formula, so where we have n and n being our number we're choosing from, so 3 and 3, 3 and 3, 3 and 3, 3 and 3, and then we say how many we're going to choose was r, so that goes here and here, so we're going to choose 0, 0, 1, 1, 2, 2, 3, 3. Then these simplify down to 3 factorial over 3 factorial, which was 1, 3 factorial over 2 factorial, which canceled out the 2 factorial part and just left that 3. 3 factorial over 2 factorial times 1 factorial, just 1. So things cancel out to give you the 3. And 3 factorial over 3 factorial times 1 factorial, everything cancels out and you get a 1. Okay, so this is the general format by which we're going to talk about combinations. If we're going to talk about how many possible things are there to choose from and how many choices are we going to make. Now, let's apply this to our boxes and our volumes. So let me bring up that picture again. Okay, so now what we're going to talk about is we're going to say that we want to think of this, think of picking between these 4 different outcomes, the a cubed, the a squared b, the ab squared, and the b cubed. We want to think of that as saying there are 4 options And in one of them, you have no zeros. In one of them, you have no B's. In one of them, you have one B. In one of them, you have two B's. And one of them, you have three B's. Okay, so that should sound kind of similar to what we were just doing over here. Okay, we're saying that we're always picking from three factors, right? It's in this case it's three A's, in this one it's two A's and a B, in this one it's A and two B's, this one it's three B's. So what we're picking from to distinguish between these things, we're picking from a total of three factors, and we're going to say I want to pick how many of them are B's, basically. So am I going to pick 0 B's? Am I going to pick 1 B? Am I going to pick 2 B's? Or am I going to pick 3 B's? Well, we know now what those outcomes are. We know that if I pick 0 things out of 3, there's one way to do it. So if I say none of my 3 factors are going to be a B, well, there's one way to do it. It's A cubed, right? A cubed is the only way to pick 0 B's. If I want to pick 1 B, well, there's 3 ways to do it. It could be A times B, it could be A times B times A, it could be B times A times A. As long as there's 1 B in there, you are picking 1 B out of those 3 factors, and there's 3 ways to do that. If you want 2 B's, well, I think it's easier just to imagine if there's going to be 2 B's in here, then one of them are going to be an A. This one could be an A, that one could be an A, or that one could be an A. Okay, so there's 3 different ways to do that. And if I want all of my factors to be B's, there's only one way to do that. Okay, so those are the coefficients, therefore, in the binomial expansion. So the coefficients from the binomial expansion, what we do to find them, if we don't want to use Pascal's triangle and just draw it out forever, is we do this formula, the combinations formula, because it will tell us how many different ways can we get each combination. It'll tell us, that there's only one way to get that combination, 3 ways to get this combination of a squared b, 3 different ways to get ab squared, 1 different way to get b cubed. This combination formula here will tell us that idea. How many of each type of solution is there going to be? And that was our goal, right? Our goal was to, if I can find where I wrote that down, our goal was to say, for a certain amount of choices, so for pick 10 out of 30, basically. Pick 10, or if you want to talk about the heads, pick 20 out of 30. Pick 15 out of 30. Okay, we want to have 30 days, and we want to pick that those factors that are being multiplied, those 30 letters, that 15 of them are R's, that 20 of them are H's. We're going to do that in the same way that I just described there. Now, let's do an example here. So, how about I see this one? We just say, how many ways, if I'm doing a 6-power expansion, so a plus b to the 6th, and there's going to be 6, am I saying that right? Let me think for a moment. Yeah, I think so. So there's going to be 6 factors in each term. It's going to be either a to the 6th, or it's going to be a to the 5th, b to the 1st. It might be a to the 4th, b to the 2nd. It might be a to the 3rd, b to the 3rd. It might be a to the 2nd, b to the 4th. They're always going to add up to 6, right? So we're going to be choosing from 6 factors, and I want 4 of them to be b's. Okay, I want to know how many of those, how many combinations can I get where 4 of the 6 factors are b's? Well, we take it to our equation. We say we're choosing from 6. We're going to divide by the amount that we choose, 4 of those factors being a b. And then we have that n minus r. Okay, right? We're looking from here, n factorial, r factorial, n minus r factorial. This is n, the number of factors I'm choosing from, for the amount of factors I'm choosing to be a b, to try to evaluate that idea, how many am I going to get? And I divide this by 6 minus 4 so that I can cancel out, I divide by the 4 factorial so I can cancel out the different combinations that give you the same thing. Anyways, sorry, I'm getting tongue-tied, but after going through this formula, we get everything cancels out other than 30, 6 times 5 over 2. So we see that there are 15 ways. Let's check our Pascal's triangle and see if that's true. Is it true that a squared b4 has a coefficient of 15? Okay, so let's look. If we go to our triangle, which we're just going to have to kind of imagine part of it here. So if we go to, this is the first power, second power, third, fourth, fifth. So we are looking for the 6. So we're looking in this row of blanks. And we're looking for the a squared b4 term. So this would be the a to the 6th term, a to the 5th term, a to the 4th, a to the 3rd. This would be the a squared b to the 4th, right? B to the 0, 1, 2, 3, 4. So we get a squared b to the 4 in this position. And look at that, 10 and 5 come together to make 15. All right, so our combination formula correctly predicted this. If we needed to predict something way, way, way down here, we could do it by simply using that combination formula. All right, let's try one last one. Let's check the neighbor here. Do we get the right one in this position? So if we wanted to choose 5 b's, out of our 6 factors, we want 5 of them to be b's. So, 0 b's, 1 b, 2 b, 3 b, 4 b's, 5 b's. Well, we would do, gotta move this. We're choosing out of 6 factors, we're choosing that 5 of them will be b's. We put it into our formula, we simplify down, and what we get, everything cancels out other than the 6, and we get the number that Pascal would have predicted, a 6 right here. All right, I believe that is all I need to say on that subject. Possibly, give me one more second to double check. Okay, so the last thing I'm going to say actually is let's apply that to our snow and rain situation. So if I want to say I'm going to have 4 days of rain, 2 days of snow, and I want to predict what that's going to be. Okay, I'm not going to use any area models. I'm not going to use any tree diagrams. I'm just going to do it from this formula. So I'm going to say I'm picking out of 6 total factors, so 6 factorial up here. I'm picking 2 of them to be snow. So I want to know how many different ways can I get 2 snow days out of 6. Well, so I have the 2 down here. I have 6 minus 2, which simplifies to 4. So this is just following our equation. And that gives me 15. So there are 15 different ways. 15 would be the coefficient in front of r to the 4th s squared. Now, if we want to know what does that mean for the overall probability, well, we just put in those probabilities. So r was 70%, s was 3%. So we're going to do 15, the starting coefficient that we had to find, times 0.7 to the 4th, times 0.3 squared. And when we multiply that out, we get 0.32 or 32%. So when somebody says on the weather, there is a 32% chance that over the next 6 days, we're going to have snow on at least 2 of them, or a third of those days we'll have snow, something like that. There's a 30% chance that a third, 2 out of 6 of our days will be snowy. This is the kind of math that is being done to find that. Okay, that is it for combinations. We're going to go through 2 fairly reasonable examples out of the book, and then kind of wrap up this whole discussion.